In this presentation, we'll discuss how to find the equivalent spring constant for mechanical systems where there are several springs and they appear either in parallel or in a series arrangement. The parallel arrangement is shown here. Springs K1 and K2 are in parallel with each other. What that means is that the ends of the springs experience the same amount of deformation with the motion of mass m. The second case is the series arrangement. This means one end of the spring is connected to another spring. In the series arrangement, both springs experience the same amount of internal force, either tension or compression. There are simple rules to find the equivalent spring stiffness for springs in parallel or in series. For springs in parallel, we simply add together the two spring constants. That is, the equivalent spring stiffness, K equivalent, is equal to K1 plus K2, where K1 and K2 are the spring constants of the two springs in parallel. For springs in series, we have to do a little bit more algebra. So if K1 and K2 are two springs in series, the equivalent spring stiffness is found by K1 times K2 divided by the quantity K1 plus K2. You'll note the following general result for K equivalent in the cases of parallel and series. K equivalent in the parallel case will always be greater than the stiffer of the two springs. So K equivalent will always be greater than either K1 or K2. For springs in series, K equivalent will always be less stiff than the least stiff spring. That is, K equivalent will always be less than K1 and it will always be less than K2. In other words, you can make a system more stiff by putting a new spring in parallel with an existing spring. But you can never make a system more stiff by putting a new spring in series with an existing spring. Students are often confused about the difference between parallel and series spring elements. In the case shown here, it's pretty easy to see what's parallel and what's series. But in some example problems, it's hard to tell. So here's the rule that you can use to try to discern the difference between spring elements that are in parallel and spring elements that are in series. In parallel spring elements, the same deformation occurs in both springs. In series spring elements, the same force occurs in both springs. That's the key distinction between parallel and series. And if you use that rule, you won't make any mistakes in handling these mechanical systems. Let's now look at an example and see if you can distinguish between parallel and series connections. So, a mass is supported by two fixed end beams of the same width and same length, and the mass is attached to these beams at their center point. The top beam has a cross-section with width W and height H1. The lower beam has a cross-section with width W and height H2. The length of both beams is L. How do we find the stiffness of this support? Are the elastic elements in series or are they in parallel? The elastic elements are in parallel since they experience the same deformation, when mass M moves up or down, both beams undergo the same amount of deflection at their midpoint. Now we can refer to the table to find the stiffness of each beam. So for the top beam, we'll have K1 equals 16E WH1 cubed over L cubed. And for the bottom beam, we'll have K2 equals 16E WH2 cubed over L cubed. Since the two beams are in parallel, to find the equivalent stiffness, we simply need to add K1 and K2. This gives us the following ideal mechanical model for our original mechanical system. We have a mass, M equivalent, on the end of a spring, K equivalent. K equivalent is the sum of K1 and K2. That will be 16E W times quantity H1 cubed plus H2 cubed divided by L cubed. And M equivalent will be the original mass, cap M, plus 38% of the mass of beam 1 and 38% of the mass of beam 2. We find the 38% for the case of a fixed beam with loading at the center. You'll find the correct amount of mass to add for the case of the free beam listed in the text by Palm. Let's now look at another example, one that is rotary. So here we have a large wheel mounted to a shaft, and the shaft is composed of two rods of equal length but different diameter. The shaft is anchored at one end to the ground. So, is this parallel or is this series? Well, if you look closely, you realize that the same torque is acting throughout both rods, and so these springs are in series. The springs have different amounts of displacement. Obviously, the thinner rod will twist more than the thicker one, but they have the same torque within them. So this case is series. We can model this as two rotary springs in series, K1 and K2, and an inertia for the wheel, which we label I. The amount of rotation of the inertia is given by the angle theta. So, if the springs are in series, we know the equivalent stiffness will be K1 times K2 over quantity K1 plus K2. And we can treat this system as simply an inertia attached to this equivalent spring. Let's look at the case where one spring is significantly stiffer than the other. And I'll pick K1 to be the stiffer one. So K1 is much greater than K2. In the parallel case, K equivalent then, which is K1 plus K2, will be approximately equal to K1. K2 will not be acting to stiffen up the parallel arrangement at all. The parallel arrangement will be acting just like the stiffer spring, K1. In the series case, K equivalent will be approximately equal to K2. In fact, it will be slightly less than K2. So we say, in the case of parallel springs, the strong spring will dictate the behavior of the system. And in the case of series springs, it's the weak spring that dictates the behavior. Finally, I'd like you to consider this. If K1 and K2 had the same stiffness, the same value of the constant, then in the parallel case, K equivalent will be 2 times K1. But in the series case, K equivalent would be 1/2 K1. So, there really is a big difference between a parallel and series arrangement of elastic elements. I want to introduce a note of caution about using the tables to find the stiffness of various elastic elements. The table results are given for particular boundary conditions, And for those results to be used, the boundary conditions have to be as specified in the table. These boundary conditions cannot be violated by some aspect of the setup. Let's consider the system below. We have one beam, marked in blue, extending from a wall. It has length L. The beam's aerial cross-section has width W and height H1. This is connected to a second beam, marked in green. It also has length L and has width W and height H2. At the end of the two beams is a lump mass. We wish to model this system as an equivalent spring and mass. So, can we treat the two beams as two spring elements in series? Here is the idea. We'll make the deflection of the first beam x1 and the deflection of the second beam x2. From the table, we can find the stiffness for the first beam. K1 equals EWH1 cubed over 4L. Then from the table, we can also find the stiffness for the second cantilever beam. K2 equals EWH2 cubed over 4L. Now, since these two elements are clearly in series, we can find K equivalent as K1 times K2 over K1 plus K2. The question I have is, does this idea work? Can we treat the two cantilever beams as springs in series? Unfortunately, this idea does not work. The problem is the boundary condition where the second beam joins the first beam is not the same as that used in the table. In the table, the boundary condition for the cantilever beam has no rotation at the wall. This is not true in the case of where beam 2 joins beam 1. At that point, the face of beam 1 has been rotated by an angle, which is beta in the diagram. So this is not the same boundary condition as in the table. If we treat these two beams as spring elements in series, the answer we get will not be correct. This system can be modeled as an equivalent stiffness with a lumped mass, but this method is not the way to find that equivalent stiffness. Let's see how well you understand this issue of boundary conditions. Let's have a pop quiz. Our question concerns this experiment. We have a lumped mass on the end of a pair of flexures. Can the flexures shown be treated as cantilever beams acting in parallel? I'll let you think about this for a moment. Let's cut to the music. Have you figured this one out? Can the lump mass with the pair of flexures be treated as a lump mass with two springs in parallel? The springs arrived at from the table by using the cantilever beams. And the answer is no. And the reason why is the boundary conditions. The problem is, in the cantilever beam in the table, the end is free to rotate. But that's not the case here. The boundary condition of the beam at the lumped mass has no rotation in this experiment. But if you look at the cantilever beam, the boundary condition at the lump mass shows rotation. Therefore, the boundary conditions in this experiment are not the same as in the cantilever beam in the table. So we cannot use the results for stiffness contained in the table for the cantilevered beam. If you were to find another table which had the stiffness of a beam with a guided end, then you would find the correct stiffness to use in this problem, and one could then treat it as two of these beams in parallel.